Assalamualaikum warahmatullahi wabarakatuh. Today, we are excited to present our assignment 2 on numerical methods for solving differential equation. We will walk you through the methods we explore, their applications, and the result we obtain. Before we begin, let us introduce our team. Sufi Nur Najiha focusing on introduction, Siti Afifah covering the programming software, Amira Saraya presenting numerical solution, Euler's methods and differential equation problem, Alfin Najiha handling coding, and Aina Fatima focusing on conclusion.
Hi, Assalamualaikum everyone. My name is Sufi Nur Najiha and my metric number 1232764. So today we are going to present to you the numerical method for solving differential equation. But first we have the introduction here, differential equation. What is differential equation? Differential equation, or we are called DE, are essential for understanding how things change over time or space in various fields like physics, biology, and economics. They help describe real-world processes like population growth, heat transfer, and electricity flow. For our assignment, we apply Euler's method. In such case, numerical method like Euler's method provide a practical solution. Euler's method is one of the simplest technique for approximating solution to ordinary differential equation. It works by dividing a continuous problem into small steps and calculating the next value based on the current slope of the function. This step-by-step process makes it a valuable tool for understanding dynamic system and solving first-order differential equations. One of the examples that use Euler's method is Newton's law of cooling. Newton's law of cooling explains how an object's temperature changes in relation to its surrounding. This principle is widely applied from designing cooling system to estimating the time of death or preserving perishable goods. Numerical methods help solve this problem effectively when exact solutions are too complicated.
So let's move to the next part, which is the programming software, where we choose Microsoft Excel. Implementing numerical techniques for solving ordinary differential equations, ODEs, is best done with Microsoft Excel, which is a popular spreadsheet program. One of Excel's main benefit it is user-friendly interface, which makes it simple for users to arrange data, carry out computations, and work with numbers without the need for sophisticated programming knowledge. It is robust built-in functions, allows users to apply formulas, conduct arithmetic operations, and employ tools like data validation and conditional formatting, all of which are helpful when putting iterative techniques like Euler's method into practice. Excel also offers practical methods for monitoring the development of a numerical solution over time by tabulating data, which makes it simple to see how the dependent variable changes as the independent variable advances. Furthermore, Excel has a wide range of visualization capabilities that greatly facilitate the interpretation of numerical data. Users can quickly create graphical representations of the solution to an OD by utilizing charting capabilities like scatter plots and line graphs. This is especially helpful when examining the behavior of the solution, since it makes it easier to see how the answer is convergent or divergent when trends are visualized or alternative approaches are compared. Additionally, SL cell referencing mechanism enables dynamic updating of value, which guarantee that the model stays flexible and adaptive by automatically updating the entire dataset and related graphs as users change parameters or enter beginning condition. So we continue with the benefits of Microsoft Excel, which is for solving increasingly complicated differential equations with more steps. Microsoft Excel's scalability allows it to handle comparatively huge datasets. Users can also use Visual Basic for applications VBA macros to automate calculations and develop custom functions for more complex tasks. Because of its increased versatility, Excel is a useful tool for both novice and expert users. Therefore, Excel's accessibility, ease of use, and visual features make it a great choice for learning and implementing numerical methods in the context of solving differential equations, even though it may not be as specialized or efficient as specialist numerical software like MATLAB or Python. So, in conclusion, even though Microsoft Excel might not be as sophisticated or effective as more sophisticated computational tools like MATLAB or Python, it provides a special blend of usability, accessibility, and adaptability that makes it a great option for solving ODs numerically, especially for novice or those looking for a more user-friendly platform. Users may effectively implement and visualize solutions to ODs thanks to its simple grid-based structure, built-in functions, and robust charting features. Excel's capabilities are further expanded from our experienced users by its support for Visual Basic for Applications VBA, which enables automation and the development of unique functions. Overall, Excel is a valuable tool for educational purposes, prototyping, and solving simpler to moderately complex ODs, providing a practical and user-friendly environment for numerical analysis.
Next, I will introduce Euler's method, a numerical technique for solving differential equations. This slide outlines the fundamental concept of how Euler's method works. On the left, we see the general form of an ordinary differential equation, dy over dt equal to f dy. This describes the rate of change of y with respect to t. In the right, we have Euler's iterative formula. Yn plus 1 equal to Yn plus h times ftn yn. This is the heart of Euler's method, showing how we use the current value of y, the step size h, and the derivative ftn yn to estimate the next value. Euler's method is a practical way to approximate solution for differential equation when finding an exact solution is not possible. It is widely used in applications where precision can be balanced with the computational efficiency. Now that we understand Euler's methods, let's apply it to a real-world scenario. Newton's law of cooling. The problem is a cup of coffee, initially T0 equal to 90 degrees Celsius, is placed in a room with an ambient temperature of TA equal 25 degrees Celsius. The cooling constant is K equal to 0.1. Use Euler's method to estimate the temperature of the coffee after 10 minutes with a step size of h equal to 1. On the right, we have Newton's law of cooling, a first-order differential equation. dt over dt equal to negative k T minus TA. Tt is temperature of the coffee at time. Ta is ambient temperature. K is a cooling constant. dt over dt is the rate of temperature change. Let's break down how we will apply Euler's method to solve the coffee cooling problem step by step. Initial temperature of the coffee is 90 degree, ambient temperature is Ta equal to 25 degrees Celsius, cooling constant is K equal to 0.1, step size H equal to 1 minute. We start with the initial condition, begin with T0 equal to 90 degrees Celsius, the temperature of the coffee at T equal to 0. Use the differential equation. Use Newton's law of cooling, dt over dt equal to negative k T minus Ta to calculate dt over dt at each step. Then apply Euler's method. Lastly, repeat and continue iterating until you reach the desired time with each 10 minutes. Now that we have the step outline, we can calculate the temperature of the coffee at each minute using Euler's methods. Let's begin with the calculation.
Part 4, Coding for Numerical Solutions. Our problem focuses on estimating the temperature of a cup of coffee cooling down in a room using Euler's method, a numerical approach to solving ordinary differential equations. The initial conditions is that the coffee starts at T0 equal to 90 degrees Celsius with the room's ambient temperature fixed at TA equal to 25 degrees Celsius. The cooling process is governed by Newton's law of cooling with a cooling constant which is K equal to 0.1. The goal is to determine the coffee's temperature after 10 minutes using a time step size of H equal to 1. Okay, so here is the programming software that we applied in our problem case to estimate the coffee's temperature after 10 minutes using Microsoft Excel. Now, let's proceed with the explanation by using Microsoft Excel. Here, Euler's method provides a way to estimate the solution to differential equations through an iterative formula which is capital Tn plus 1 equal to capital Tn plus with h time with the function of small tn with capital Tn, where the function represents the rate of change of temperature. In this case, the cooling function is given by function of small tn with capital Tn equal to negative k times with bracket capital Tn minus with capital Ta. Substituting the given parameters and the function becomes negative 0.1 times with the bracket capital Tn minus 25. Using h equal to 1, we can calculate capital Tn plus 1 for successive time steps starting from the initial condition 090. For example, at the initial temperature 090, the rate of cooling is negative 6.5. The next temperature T1 is calculated as T1 equal to T initial plus with H time with the function of the rate of cooling equal to 90 plus 1 times with the negative 6.5, and we got T1 equal to 83.5 degrees Celsius. This process is repeated for each subsequent minute and the results are tabulated. By continuing this iterative process for 10 minutes, the temperatures are calculated step by step. The table in the Excel sheet shows the result for each time step, including the time, temperature, and the rate of cooling. The Excel formulas used to perform these calculations are straightforward. The formula for function small tn and capital Tn is negative 0.1 times with bracket capital Tn minus 25. And the formula for capital Tn plus 1 is capital Tn plus h times with the function of small tn with capital Tn. So, here is the graph illustrates the result of estimating the coffee's temperature over a period of 10 minutes using Euler's method. Initially, at T equal to 0, the coffee starts at a temperature of 90 degrees Celsius. As time progresses, the coffee cools down due to the difference between its temperature and the ambient room temperature of 25 degrees Celsius. By the end of 10 minutes, T equal to 0, the estimated temperature of the coffee has dropped to 47.66 degrees Celsius, as shown by the data points and the graph. The curve reflects the exponential cooling behavior predicted by Newton's law of cooling, where the rate of temperature decrease slows as the coffee approaches the ambient temperature. This visual representation confirms the calculated values and effectively demonstrated how the coffee cools over time. Next, exact solution. The exact solution to the coffee cooling problem is derived from Newton's law of cooling, which is described by the differential equation dt over dt equal to negative 0.1 times with bracket T minus 25. Here, capital T is the coffee's temperature, small t is time, and 25 degrees Celsius is the ambient room temperature. The equation states that the rate of cooling is proportional to the difference between the coffee's temperature and the ambient temperature. To solve this equation, we start by separating the variables, dividing both sides by T minus 25 and multiplying by dt. We get 1 over T minus 25 dt equal to negative 0.1 dt. Next, we integrate both sides. On the left, we will get ln T minus 25, and on the right, we will get negative 0.1 T plus C, where C is the constant. After exponentiating both sides to remove the natural logarithm, we find that t minus 25 equal to exponent the power of c times with exponent the power of negative 0.1t. For simplicity, we let a equal to exponent the power of c. So the general solution becomes tt equal to 25 plus a times with exponent the power of negative 0.1t. To determine the value of a, we use the initial condition, which is 090. Substituting t equal to 0 into the equation, we get 90 equal to 25 plus a times with exponent the power of 0. Since exponent the power of 0 equal to 1, this simplifies to a equal to 90 minus 25 and a equal to 65. Substituting a back into the general solution, we obtain the specific formula tt equal to 25 plus 65 times exponential the power of negative 0.1t. To find the coffee's temperature after 10 minutes, we substitute t equal to 10 into the equation. This gives T10 equal to 25 plus 65 times exponent negative 1. Using the approximation, we calculate T10 equal to 48.91 degrees Celsius. Finally, we can compare the result to estimate from Euler's method. We see that the exact solution predicts a temperature of 48.91 degrees Celsius, while Euler's method gives 47.66 degrees Celsius. The small difference is due to the approximation used in Euler's method, while the exact solution is derived directly from the differential equation. This graph illustrates the comparison between the results of Euler's method and the exact solution for the coffee cooling problem. The blue line with points represents the approximation obtained using Euler's method, while the red line represents the exact solution derived from solving the differential equation. As observed, the two lines closely follow the same trend, showing a gradual decrease in temperature over time as the coffee cools down. Euler's method provides a step-by-step approximation based on the given step size, which result in discrete points that are slightly off from the exact solution curve. Despite this minor deviation, the Euler approximation aligns well with the exact solution, confirming its reliability for estimating the temperature within acceptable error limits.
For the conclusion, in this assignment, we used Euler approach to solve Newton's law of cooling and predict the temperature of a cup of coffee over time. The problem indicates the initial temperature of the coffee 90 Celsius, the ambient temperature 25 Celsius, and the cooling constant 0.1. We used Euler approach with a 1-minute step size to repeatedly calculate the temperature at each minute for up to 10 minutes. The coffee estimated temperature after 10 minutes was 45.40 Celsius. This numerical method enables us to approximate the solution to the differential equation that regulates the cooling process, resulting in an efficient method for estimating temperature at discrete time intervals. Euler's method, while basic, provides a good approximation for such problems, particularly when obtaining a more exact solution, for example, by analytical method, is difficult. However, it is crucial to remember that Euler's approach can accumulate error with greater step size. Therefore, selecting a smaller step size will enhance the solution correctness. This exercise highlights how numerical method may be applied to address real-world problems, such as estimating an object cooling rate over time. It also demonstrated the usefulness and limitation of Euler's approach for solving ordinary differential equations in a variety of applications.